Okay, good morning. So we're headed toward the end of chapter 8 now, which is the end of the first chapter on chemical bonding. And our next chapter will be chapter 9, which is more advanced topics in chemical bonding. And so what we've done so far, we've talked a lot about drawing Lewis structures based on the idea of covalent bonding, the electrons tending to form pairs to hold nuclei together. Remember, the idea is essentially that you have a nucleus of one atom, you have a nucleus of another atom, and these electrons will form waves around the nuclei. And since the electrons are negatively charged, they will hold the nuclei together. And you've got a covalent bond. And so, we generally represent this with a straight line notation between two different atoms. And notice it's a pair of electrons, two of them. Okay, that's a quantum mechanical effect. We'll get a little bit more into that in chapter 9. The idea that atomic orbitals, or what we call molecular orbitals, according to the Pauli exclusion principle, can possess up to 2 electrons of opposites, with those two having opposite spin. But we also noticed that there's a tendency for the atoms to form bonds in such a way that they, in a sense, I forgot argon there, they mimic the noble gases. Okay, so for example, hydrogen will come together to form one bond such that each electron is sharing 2 electrons, which is the number of electrons that helium has in its valence shell. Likewise, oxygen will tend to share 4 electrons, 2 bonds with itself, or with not with itself, but with another oxygen atom, giving each atom 8 electrons, which gives it the same number of valence electrons as neon does. Likewise, sulfur will often form structures such that it also has 8 electrons, giving it the same number of valence electrons as argon, and so forth and so on. And we called this the Octet Rule. What we're going to look at today are what we would call exceptions to the Octet Rule. And this is still an area of research that is somewhat undergoing for some substances to determine the validity of this Octet Rule under some circumstances. Is it always the case? And it turns out the answer seems to be no. It does not seem to be a universal law, but it is pretty common. So we're going to look at some exceptions here, section 8.8. Okay. So what I'm going to do is I'm going to point out a couple of elements that are what we would call, would exhibit, exceptional behavior. So the first one we're going to look at is beryllium. So I'm going to circle this element right here. This is in group 2A. And what is observed with beryllium is that it seems to be able to form a covalent bond to 2 separate atoms, okay, in such a way that it has a total of 4 valence electrons. Okay, so one thing you just want to do is say, hey, beryllium is an exception. It tends to form 4 valence electrons, or have 4 valence electrons. Now, there has been some discussion as to whether you could get resonance here. So you push a pair of electrons from each of the fluorines. Kind of makes sense, right? That's sort of like what we talked about in terms of the Octet Rule. That's how we drew Lewis structures. Sorry, I guess yeah, no, I had that right. Okay, But there's some evidence that this doesn't happen. Okay, so I'll put a little question mark there. So in general, the acceptable structure for beryllium is that it has 4 valence electrons and a covalent bond to each of the surrounding atoms. Okay. It does tend to have a valence of 2, meaning it forms a bond to 2 separate atoms. Okay, so that's the first one. The second one, coming over all the way to group 3A, I'm ignoring the transition metals because we don't tend to draw Lewis structures for them, is boron, and below that is aluminum. So again, okay, so I'll put a little check here. This is what you want to draw, and I'm going to get rid of the arrows and kind of the busyness that I drew in there. There we go. Okay. Notice fluorine does obey the octet rule in that structure. So that's the one we have there. So now the case of boron and aluminum is very interesting. So boron and aluminum each have 3 valence electrons. And what they seem to do very commonly is to form a single bond to 3 surrounding atoms. So we might say it has a valence of 3. And then this is fewer than 8 electrons around the boron, right? So remember, with the covalent bond, each atom donates 1 electron, and then those 2 electrons come together to form a bond, okay? So boron had 1 electron, 2 electrons, 3, but each fluorine had an additional electron. So that gives you a total of 6 in terms of bonding, okay? So same thing with aluminum. Aluminum does essentially the same thing. Okay, again, people will try to study to see if there's any double bonds in here. And the jury is, I think, out even today. Okay, so what do we see? We're seeing 6 electrons around those 2 elements. So right there. So if you want, you can just write like, you know, there's your exception, 4 electrons for the beryllium, and then 6 electrons for the boron and aluminum. Now, keep in mind, this actually, some evidence that this leads to interesting chemistry would be that if you take the boron, and I'm going to draw the Lewis structure like this. Okay. If we take another substance, in this case, it's going to be a fluoride ion, which has 8 valence electrons. So this is F minus. Oops, I'm going to write F minus, just want to write minus. Right, so it's got that extra additional, you know, fluorine is in group 7A, so it has 7 electrons. This gives it 1 more, it's got 8. So what can happen is you can form a bond. This pair of electrons can attach essentially to an empty atomic orbital on the boron. And then you get a chemical reaction. And this happens. There's actually a chemical reaction between these 2 substances. Aluminum behaves similarly. Sorry about everything getting kind of busy in there. So now you have a new bond to a new atom. Now it's bringing in a negative charge. So I'll put the negative right there. Okay. So notice what happened. Now you got your octet, right? So there is some evidence that this happens, that, you know, the boron, because it only has 6 electrons, a pair of electrons coming from, I'm not going to use the terminology that people use, but a pair of electrons coming in from the fluoride can attach to that boron and then give the boron the 8 electrons. So both structures do exist. There is a BF3, it does exist. You can produce it, you can work with it. But there's also a BF4 minus, right? So this is BF3 plus F minus going to BF4 minus, right? And so again, boron and aluminum, they tend to have 6 electrons, but they have the capacity to react with something that has extra electrons and then have 8, okay? So those are often referred to, these 3 elements, as beryllium, boron, and aluminum, as electron deficient. Just meaning like, look, they have fewer than 8 electrons, they're deficient of the octet. Okay, but that appears to be the case. So just memorize those 3. More broadly, though, we're now going to look at the second group. And the second group will consist of the third row and beyond, third, fourth, fifth, sixth, however far you want to go, non-metals. So phosphorus, sulfur, chlorine, arsenic, selenium, bromine, tellurium, and iodine, and even some of the noble gases like xenon and radon and even krypton. So third row, we would start with phosphorus. This is the first element we tend to see evidence for this. We're now going to talk about another kind of rule breaking, which we're going to call expanded octets. Okay, so these are, again, exceptions, and there's evidence that these structures exist, although, again, like I said at the beginning, it's not universal agreement on this. There are other hypotheses about what's actually happening. So I'm going to start in the third row. We're just dealing with the third row non-metals and beyond, fourth row, fifth row, sixth row. We're going to start with phosphorus, which is in group 5A, sulfur, which is in 6A, chlorine, which is in 7A, and then coming down to the next column, we have arsenic, selenium, bromine, and now I'm going to add in krypton. Okay, I'm not going to add in argon. And then below that, we've got antimony, tellurium, iodine, and xenon. And those are the elements that I want to focus on. By the way, this is group 8A. Okay. So, I've kind of made this as simple as I can. It looks like we're talking about 4 of the families, 4 of the columns, and 3 of the rows. I mean, there could be some others included in there as well, but for the most part, these are the ones we'll focus on. So these elements are capable of having what we call expanded octet. Expanded meaning greater than, so greater than 8, right? So again, pairs of electrons, 10 electrons, 12 electrons, that sort of thing, okay? This is not xenon, by the way. I'm just, this is nothing. Okay, I'm not including that one, okay? Expanded octet. Now, the key to this is that it has to be the central atom, okay? That's important. If one of these elements is the central atom, it is capable of having more than 8 electrons. If it's a surrounding atom, then no, that's not the case. So for example, if I have SCl2, chlorine is in this group that I'm highlighting, right? But they're surrounding here. Those are surrounding atoms. So no expanded octet for chlorine. But sulfur is in the center, right? It is. It's right there in the center. So it could be. So possibly. Okay. So let me show you an example of what I mean by this. If you draw PCl5, there is no way to draw that as an octet with the phosphorus. It's just, there's no way to do it. Well, there is a way to do it. I'm not going to talk about it in this course. If you take more advanced chemistry, you would learn about it. This is essentially the simplest Lewis structure you can draw, and it gives you 8 valence electrons. I'm sorry, 8 valence electrons around all the chlorines. Remember, the chlorines are surrounding here, so they are going to have 8. So you're not going to break the octet rule for surrounding atoms, only for the central atom. So each of these chlorines is going to have 3 lone pairs and 1 single bond, okay? But notice the phosphorus, it has 10 electrons, 10 valence electrons. 2, 4, 6, 8, 10. But how are you going to draw that if you have 5 chlorines and each one has to have a bond? You would have to have one of the chlorines not have a bond, and then it wouldn't be part of the structure. So you have to have an expanded octet there. In general, we can show that the expanded octet might be justifiable using formal charge. If I look at the phosphorus in terms of its formal charge, remember? Okay, I know I just covered that yesterday, but you can review it if you want. You take the number of valence electrons and you subtract the number of associated electrons, right? And the associated electrons were lone pair electrons. You get 2, and then a bond is 1. The phosphorus doesn't have any lone pairs, but it has 5 bonds. Phosphorus is in group 5A, so it's 5 valence electrons minus no lone pairs plus 5 bonds. Look what you get. You get 0. It has a formal charge of 0. So sometimes we justify the possibility of a expanded octet. You can also use that for electron deficient, but we justify it based on the idea that, hey, if you have an expanded octet, that gives you a formal charge of 0. So that's our primary justification for exceptions to the octet rule, is formal charge ends up being 0. And remember what we said yesterday, the closer the formal charge is to 0, the better. So in PCl5, phosphorus pentafluoride, doesn't appear to be any other way that you could draw the Lewis structure. You got to have 5 bonds. So you got 10 electrons around the phosphorus, but guess what? That gives it a formal charge of 0. Okay. So let's take a look at a couple of examples here on Alex. Oops. There we go. Popped up. Recognizing exceptions to the octet rule, determine whether the Lewis structure proposed for each molecule is reasonable or not. Okay. So let's take a look at the first one. The first one is oxygen. All oxygen, this is ozone, by the way. 3 oxygen atoms. Okay. Well, that's not in the third row. It's in the second row. So it's not going to be an expanded octet. You're not going to have to worry about that. So octet rule should be in force here, right? And it's not boron or beryllium or aluminum, one of those 3 elements. So let's take a look. First of all, oxygen should have 6 valence electrons because it's in group 6A, and there are 3 oxygens, right? So it's O3. I'm looking at the molecule in the first column, O3. So 3 times 6 is 18. So one of the things you want to do is see if you got 18 electrons. Remember, each lone pair is 2, each bond is 2. So 2, 4, 6, 8, 10, 12. There's 12 electrons in the lone pairs, 2, 4, 6 in the bonds. That's 18. So it's got the correct number of electrons. That's cool. Correct number of valence electrons. So we would not say no, the total number of valence electrons is wrong. So we don't put the correct number for that one. Now we look at the Lewis structure in terms of the octet rule. Again, it's oxygen, second row should have octet rule. The oxygen on the left definitely has 8, right? 2 bonds and 2 lone pairs. The oxygen in the center has 8. It has 3 bonds and a pair, right? Well, in terms of the octet rule, you count all the electrons around the atom. The oxygen on the right has 2, 4, 6 in the form of lone pairs plus 2 in the form of a bond. That's good. So it's actually, yes, it's a reasonable structure. The oxygen is fulfilling the octet rule for each oxygen. Remember, you got to check all of them. And it has the correct number of valence electrons. So we're set. Okay. Let's look at the second one. The second one is SF4. Okay, that's a molecule, not an ion. Sulfur is in group 6A, right below oxygen. So it has 6 valence electrons. Fluorine is in group 7A, so it's got 7 valence electrons. 7 times 4 is 28, plus the 6 from the sulfur is 28 plus 6 is 34. It should have 34 electrons. So let's check to see if it has 34. It looks like it does, right? So here's how I'm counting them, just so that you know. What I would do, just to do it quickly, because my eyes are not real good, but what I would do is I would look at each fluorine and notice they each have 8. So there's 8 there. There's another 8 there, 16. Another 8 there, 24. Another 8 there, 32. And then 34, right? And that's what we wanted, right? We wanted 34 valence electrons. Now, what you notice is that the sulfur has 10. Right? So it doesn't have 8. This appears to be a violation of the octet rule. But if you look at the formal charge calculation, remember, formal charge is valence electrons in the periodic table. So sulfur has 6 minus the associated electrons. The associated electrons is the lone pair. So if sulfur has one lone pair, that's 2. Remember, the lone pair counts as 2 in formal charge calculation. But a bond only counts as 1. So it's 2 plus 4 is 6. So it's 6 valence electrons minus 6 associated electrons. 6 minus 6 is 0. Hey, we've got a justification here for an expanded octet, right? Sulfur is a third row element. It's one of those elements I mentioned. It's central atom. It's got to be the central atom. And it has a formal charge of 0 in this structure. Again, it has to have the correct number of valence electrons. You can't make it work out just so that everything's either octet or expanded octet, but have the wrong number of valence electrons. That's all got to be, keyed in properly. Looks good. It's a reasonable structure, SF4. Now, the last one is OF2. This one actually looks, well, I don't know. Let's see. Let's take a look. It seems to have a lot of electrons. Oxygen, so it's O, so that's 6. Fluorine is 7, right? It's in group 7A. So 2 times 7 is 14 plus 6 is 20. 20 valence. Do we have 20? I don't know if we do. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We do. There's 20 electrons. Oh, man, this looks great, right? There's a problem with this Lewis structure. It's actually staring at us right in the face. It has the correct number of electrons, but look at that oxygen at the center. It has 2, 4, 6, 8, 10, 12 electrons. It's a group 2 element. If it were sulfur, this could be possible, right? It might work out okay. But the oxygen is a second row element. You don't see expanded octet until you get to the third row. Now, the general argument for that is that the reason you can have expanded octet with the third row is that you've got third row means you can have 3D orbitals. So if you have an extra 5 3D orbitals, there's space to put extra electrons around the nucleus. That argument is a little tenuous, and again, many people disagree with it. But the point is, when we're in the second row, we cannot have an expanded octet. It's a general rule of thumb for those of you that go on to organic chemistry that a Lewis structure with more than 8 electrons around a carbon atom is a no-no. Well, things are more complicated than that. But for now, we want to say that. We want to say that the second row elements would not have more than 8 electrons. So the problem here is there is a problem. Some atoms have the wrong number of electrons. The oxygen, right? The oxygen is the problem. The fluorine seems okay. There is a problem with how the fluorine's working out here, but each fluorine has the correct number of electrons. That's okay. So we would just say that it's the oxygen that's the problem. Okay. Let me show you one more. Okay, so here's our phosphate ion. Now it's an ion, right? Remember, when it's an ion, you got to either add or subtract electrons. This is negative, so you add the electrons. Phosphorus is in group 5A. Oxygen is in group 6A. So 5 plus, I'm just going to do 5 plus 3. Let's do that first because that's easy. 5 plus 3 is 8. And then you got 4 times 6. So 24 plus 8 is 32. So we should have 32 electrons. So notice they put the brackets, that's good. And they put the charge outside the brackets, that's good. Okay, phosphorus, third row, could have more than 8. Nothing wrong with having more than 8, as long as the formal charge gets close to 0. So let's check that out first. I know that, really you want to check the number of electrons. Well, actually, okay, let's check the number of electrons first. Around this oxygen, there are 8. Around this oxygen, there are 8. Around this oxygen, there are 8. And around this oxygen, there are 8. And there's no lone pairs on the phosphorus. So that's 32 right there. We're good. 8, 16, 24, 32. Okay. In American football, you count by 7s. Sometimes you count by 6s, but usually you count by 7s. In Lewis structures, you tend to count by 8s, 6s and 8s. Okay. So we got 8 electrons around each oxygen, so that adds up to 32. So we got the correct number of electrons. Now, let's do the oxygens. Each oxygen has 8, so that's good. Nothing wrong with that. Shouldn't have more than 8. Shouldn't have less than 8. Greater or fewer. Phosphorus. Now, this one has more than 8, right? So is that a problem? It was a problem for the oxygen, but phosphorus is in the third row. So it maybe can have more than 8. So how many does it have? 2, 4, 6, 8, 10, 12. That's a lot, right? 12 is a lot more than 8. But let's do our, whatchamacallit, the formal charge calculation. Phosphorus is in group 5A, so that's 5. Let's see, it has 5 valence electrons. It has 6 bonds. So that gives it a formal charge of -1. Now that's interesting. It has a formal charge not of 0, but -1. Now, one of the things that I can't recall if I mentioned when it comes to formal charges is that if you're drawing Lewis structures and one of the atoms has to have a negative formal charge, there's just no way around it, the more electronegative atom should have the negative formal charge. So oxygen is the second most electronegative element in the periodic table. Fluorine's number 1. So if there's a negative formal charge, it should be on the fluorine. But if you have oxygen in another element, the negative formal charge should be on the oxygen. Remember that electronegativity comes into play with Lewis structures. Okay, so oxygen is more electronegative than phosphorus. So this is actually a problem, because the problem is the phosphorus. And I would say no, some atoms have the wrong number of electrons around them, and the problem is the phosphorus. The phosphorus would be okay with 10. So if you pushed one of these bonds back onto this oxygen and gave the oxygen the negative formal charge, the phosphorus would now have 5 bonds. And so 5 minus 5 would give you 0. So it's almost right. This one, notice the nuance. In fact, this one is so interesting in terms of the nuance. I want to show it to you. Let me come over here and show you the correct structure. Okay, so this is phosphate. Okay, so one possibility would be this. Now that's got an octet around the phosphorus, but that's problematic because your formal charge of phosphorus would be 5 minus 4, which is +1, right? 4 bond, doesn't have any lone pairs, so it's just 5 minus 4. Now, the one they showed was they put a double bond on 3 of the oxygen, on 2 of the oxygens, right? And not 3, 2. Okay, now here's the problem for phosphorus. It's 5 minus 6. And that's -1. So really what you're doing is you're saying this oxygen here, oh, I'm sorry, I drew an extra pair there. Are going to have a formal charge of 0, but this one's going to be -1. That's a problem because the electronegativity goes in the following order. Fluorine is greater than oxygen, which is greater than nitrogen, which is equal to chlorine, right? Remember it was 4.0, 3.5, and then 3.0. But phosphorus is below nitrogen. It's actually like 2.1. So oxygen is much more electronegative than phosphorus is. So if you have a negative formal charge, the negative formal charge should be on the more electronegative atom. So negative formal charge should be on the more electronegative atom. Okay, which is oxygen in this case. So how do we deal with that? You just take one of these oxygens that has a double bond and push a pair out. So here's the correct structure. Single bond, single bond, single bond, double bond. So now 3 of the oxygens have a -1. This one's a 0, and this one's a 0. And note, when you draw these Lewis structures, if you add up all the if you add up all of the formal charges, they will equal the charge of the ion. So if you have a charge of -3, adding all these formal charges should add up to -3. Now they did in all of these cases, but this is the correct structure because you get the formal charge on the phosphorus, okay? So octet rule for second row, like oxygen, fluorine, carbon, nitrogen. But formal charge of 0 for the third row and below, if it's the central atom. Remember, it's the central atom that we're talking about here. So there you go. So that one was almost right. It was close, but it wasn't quite there because of that phosphorus having an extra bond in here to this oxygen, either one. Okay. BEH2, this one looks good. I just, why? Well, it's got 4 electrons. Beryllium is in group 2A, so it has 2. Hydrogen is in group 1A, so each one has 1. So that's a total of 4. It's got the correct number of electrons. But remember what we said, beryllium's going to have 4. It's got 4. Now you can do a formal charge calculation. Beryllium has 2 valence electrons. In this structure, it has no lone pairs, but it has 2 bonds. So 2 minus 2 is 0. It's got a formal charge of 0. You can also check hydrogen. Hydrogen with 1 bond will have a formal charge of 0 because it's 1 minus 1. So that's cool. That one's okay. This one's a problem. Carbon, just looking at it, stares in your face, right? Carbon doesn't have the correct number of electrons. The whole structure probably doesn't have enough electrons. Let's see. Carbon has 4. Oxygen has 6. So 6 times 2 is 12 plus 4 is 16. 2, 4, 6, 8, 10, 12. So it has, the total number of electrons is wrong. The correct number should be 16. Some number of electrons have they're just, wrong. So oxygen is wrong. So that's an O. Carbon is wrong. That's a C. Oxygen is wrong. That's an O. It says down here, for example, if 2 oxygen atoms have the wrong number of electrons around them, enter it twice, right? So you would put, C, O, O, or O, C, O. Just make sure you get that in. Okay, and there you go. All right. So those are the exceptions. There's one other type of problem in here that I would like to show you. And that is to show you a expanded octet where you actually draw the Lewis structure. So be careful. This one sometimes gives people a problem just because of how you enter it into ALEX. So practice, look for tutorials and stuff like that. If you really have a problem, get entering it into contact support. Probably can't do this on a phone, I would assume. So draw the Lewis structure for Br3 minus sign, right? It tells you it's expanded octet of the central atom, right? So let's take a look at that one. Okay, bromine is in group 7A, so 3 times 7. There's 3 bromines, each one has 7 valence electrons, but there's a charge of negative, so you have 1 more. 22 valence electrons. Okay, so how do we draw this? Don't draw a ring. Rings are relatively rare if you only have 3 atoms. It is possible, but I've only seen it with carbon, and it's explosive. Okay, remember, whatever Lewis structure we come up with, we got to have the brackets with the charge outside of it. Okay, so we've already thrown in 4 electrons right there because of the 2 bonds. So, minus 4, so 22 minus 4 is 18. Put them on the surrounding atoms till they're up to 8. Remember, surrounding atoms will never go beyond 8. So I've just done 16. I'm going to put another 2 here. Okay, so minus 16. Oh, sorry. minus 12. Ooh, wow. And then, oh my goodness. Okay, so let me come back here. I've done the surrounding atoms, but I just added another 12. So that's still got 6 left over. So you have to put them on the central atom, right? I mean, you got to use all the electrons. So I did 4 for these two, right? 4 for the bonds. And then 6 for each surrounding bromine, right? Because you want to get the surrounding atoms up to 8. You don't want to go beyond 8. So you stop by putting 3 lone pairs on each. So that's 12 because there's 2 of them. But that still left us, let me just make sure I got the correct number of electrons here. I might be off a little bit. Let me make sure. 7 times 3 is 21 plus 1 is 22. 22 minus 4 is 18. 18 minus 12 is 6. So now you got to put 6 on a central atom. Okay. So that's 1822 electrons. Okay. So I've distributed the electrons. Now, what's going on here? Well, the surrounding atoms are cool. They've got 8 electrons. That's not a problem. The central atom has a lot more than 8, right? It's got 2, 4, 6, 8, 10. Well, not a lot more. It's got 10. So the central atom. So what do? You say, well, wait a minute. The central atom, 3rd row and beyond, is okay to have more than 8. Bromine is in the 4th row, so that's okay. It's okay for bromine to have more than 8, but let's do a formal charge. Seven valence electrons minus 2 bonds plus 6 lone pair electrons. So you get 7 minus 8, which is minus 1. So that one's minus 1. This is 0. This one is 0. Well, they add up to -1. That's okay. Is there any way that you could draw this at the, something has to be negative? Because again, the formal charges have to add up to the charge of the ion. So if the charge of the ion is -1, something's going to have to be -1. So you have a choice. It could be the bromine on the left, the bromine on the right, or the bromine in the center. But like we said, expanded octet should be on the central atom only. So this looks like a good Lewis structure. That's perfectly fine there. Okay. Let's take a look at one more. Okay, again, expanded octet of ClF3. So notice the expanded octet shows up a lot with like when the surrounding oxygens are fluorine and oxygen. And there's a key to actually what's happening. The most electronegative atoms are forming the substances that have expanded octet. Now, this is called chlorine trifluoride in this example. It says, write the Lewis structure for an expanded valence shell central atom. It's telling you, make the central atom expanded octet, okay? So that's kind of nice of them. Chlorine's in group 7A, so is fluorine. So it's 7 plus 3 times 7. So that's what? 21 plus 7 is 28 valence electrons. It's ClF3. So we put the chlorine in the center. Think of a box. Fluorine's on the box. Probably going to have a lone pair somewhere in that chlorine. So now 28 minus 6. Why 6? Because we did 3 bonds. A bond is 2, and there's 3 bonds, so that's 6. Now fill out the surrounding atoms to up to 8. Octet rule for the surrounding atoms. By the way, that's not a dot. Oh, maybe you can't even see it on your screen. Okay, so fill them out. That's 18, right? I just put 18. So you got 4 left. Where are they going to go? They got to go on the central atom. So generally what you do then is you just kind of draw them a little ways away from each other. We'll talk more about how this appears when we do structures in chapter 9. So now what do we have? Well, it's neutral. So the formal charges should add up to 0. Okay. So formal charges add to 0 because it doesn't have any charge. Well, this one has a formal charge of 0. How do I know that? You can go through it. For the fluorine, formal charge equals 7 valence electrons minus 6 electrons in the form of a lone pair in a bond. 7 minus 7 equals 0, right? We did that yesterday, so this is 0. But if you look at the electronic structure of each of the fluorine atoms, they're all the same. They all have 3 lone pairs and 1 single bond, so they all have a value of 0. So that means the chlorine is going to have to work out to 0, right? If all those are 0 and they got to add up to 0, 0 plus 0 plus 0 plus x equals 0, you know that x has got to be 0, right? So it's got to be 0. So let's see. Chlorine has 7 valence electrons, minus it's got 2 lone pairs, so that's 4, and 3 bonds, which is 3. 7 minus 7 equals 0. And there you go. Cool. We got it. All right. So those are expanded octet problems. There's 2 different types you want to work on, and they're kind of fun. Practice doing Lewis structures. Again, for those of you that are going to go on to take organic chemistry, so if you're in any of these kind of pre-professional, actually every biology major to get a bachelor's degree is supposed to take organic chemistry, a year of it. Although I think there are a couple schools that are kind of being funny about that. You'll need to do organic chemistry. So organic chemistry, it all starts with drawing these Lewis structures and expanded octet and all of that. Okay. So the last topic is 8.9. Last topic of this chapter is 8.9. And it's called bond energies. Although technically it's enthalpies. Okay, so here's the idea. We talked about bond strength earlier in the week and last week. This idea of bond strength. It is possible to take a molecule and in the gas phase, put in energy to break it into individual atoms. Okay? So another way of writing this would be 2H, right? Okay, but it takes energy to break a bond. So breaking a bond is endothermic, right? It means it requires energy. And that makes sense, right? Like things don't break on their own, you have to break them. So it takes energy to break them. Okay. Now, this is not as obvious, but it's also very important, which is that forming a bond is exothermic. That's not obvious. This is not obvious to me. Energy is released. So if I were to take this reaction 2H and go back the other way, you would get energy out. It's an exothermic process. So producing a chemical bond is exothermic. Okay, kind of cool. Now, you can measure these. They're measurable. What you do is essentially you come up with, you put the substance into the gas phase, you fill up a container that has, windows that light can go through. Okay, and then you shine lasers in. And because, energy equals hc over lambda, if you know the wavelength of the light you're using, you know the energy of the photon, and, you got your H2 in here as a gas, you just measure what wavelength of light breaks the chemical bonds. And there's a way to detect that the chemical bonds have been broken and stuff. Okay, you can measure it. And so in practice, what you do is you measure the energy it takes to break the bond. It's harder to measure the energy released when a bond is formed, but we know from chapter 5, thermochemistry, that the reverse of an equation just reverses the sign of delta H. Okay, so forming a bond is exothermic, energy will be released. Breaking a bond is endothermic, it requires energy. Okay, so that means we can actually create all sorts of values for chemical bonds because they can be measured. So what I'm going to do is I'm going to write down a few of these. So this bond has an energy of 436. So these are I'm going to call them delta H in kilojoules per mole. And what this says is if you have a mole of H2, the amount of energy that it takes to break all of the bonds in that one mole, 6 times 10 to the 23rd molecules, is 436 kilojoules. Okay. The chlorine molecule, ClCl, that one is a weaker bond. It only requires 243 kilojoules per mole. Now here's another example, HCl. I'm just getting these out of a table. You can find them all over the internet, but use the Alex values. I kind of like the Alex values because they don't go to like 0.01 and stuff like that. They just give you nice round numbers, 862, which is perfectly fine. Okay. So there's a few. Let me show you another one. A couple more. So CH is 413. And O double bond O is 498. And C double bond O is that double bond O? 1077. That seems a little high. I'm sorry. I think it's a triple bond. 1077. And OH is 497. That seems to make sense. Okay, so there's a few. I'm just kind of writing down a few of them just so that we see how to use them. O double bond O, I've got that one at 498. Okay. Good. Okay, so I'm going to show you. So you got these values here. Okay, so let me save this. Okay, and again, these are called bond enthalpies or bond energies. And now what I want to do is I want to show you an example problem. Okay. Calculating the heat of reaction from bond energies. Calculate the heat of reaction delta H for the following reaction. 2 CH4 gas plus 3 O2 gas forms 2 CO gas plus 4 H2O gas. You can find the table of bond energies by using the data button on the Alex toolbar. Round your answer to the nearest kilojoule per mole, which is nice. Just round it to the nearest kilojoule. Okay, so this one right here is a combustion of methane to form carbon monoxide and water. Okay, so let me bring this up. Okay, so here's the reaction. 2CH4 plus O2 goes to 2CO plus 4H2O. Everything's gas phase. So these calculations are all in the gas phase. I think I need, was it 3 oxygens, right? Yeah, 3 O2. There we go. Okay. So there you go. So everything is only work. These calculations only work because in the gas phase, because all of these values are calculated in gas phase. Okay. So how do you find delta H of the reaction, delta H? So here's how you calculate it. I'm going to write a formula down for you. It's the sum of the number of moles of each product. So PR for product times the bond energy of that product. Okay, so you're going to add up. That symbol sigma, the uppercase sigma means add up sum. So let me put this in parentheses just so you can kind of see how it works, not get confused. Minus the sum of the number of moles of each reactant times the bond energy or bond enthalpy of each reactant. So what you're going to do is you're going to look up all the bond energies of all the products, you're going to multiply the coefficient. Okay, so there's your coefficient times each bond energy, coefficient times each bond energy, and add them up. So you can do that for products first, then you're going to do it for reactants, and then you're going to take the difference. Okay, so let me first begin by drawing a Lewis structure so that we know what bonds we're talking about. I'm going to do the Lewis structure for CH4. Now I'm just going to write them down. You know, when you're doing these problems, may not be an expert on drawing Lewis structures, so it might take you quite a bit longer to write them, but that's just part of how the problem works. So there's the Lewis structure for methane. Okay. So if you look at the methane molecule, it just has CH bonds. That's the only type of bond in that molecule. Okay. So we're going to have to look up that value for CH. Now, how many CHs are there? Well, there's 1, 2, 3, 4, but there's 2 of these. So it's 2 times 4. So that's 8 bonds, right? There's 4 for each CH4, but there's 2 CH4, so that's a total of 8. So when we look that value up, we're going to multiply it by 8. Now let's do the O2. The O2, I'm doing the reactants, just, you know, the Lewis structures of the reactants first. Okay, look at that type of bond. Now be very careful when you do this. Don't look up single bonds. This is a double bond. It's 1 double bond, not 2 single bonds is not equal to 1 double bond. It's a double bond. But we have 3 O2s, so we need 3 double bonds for oxygen, okay? I'm going to look the values up in a little bit. So those are the reactants. Now I'm going to do the products. So the first one is CO. This is the Lewis structure for CO. Okay. It's a triple bond. It's 1 triple bond, but you've got 2 of them. So 2 triple bonds, right? 2C double triple O. Double bondo, triple bondo, C triple bondo. Okay. Because you got the 2 there. That's where that 2 comes from. Now, what about the water? Well, we know what water is, H2O, right? Okay, we're not worried about the Lewis. We're not worried about the lone pairs. We're just worried about the bonds. So how many bonds are in there? 2 bonds. 2 single bonds, but there's 4 waters. So 2 times 4 equals 8 bonds. And that's the OH bond. Okay, so now we've got 4 different bonds we have to look up. We need to look up the CH bond. We need to look up the O double bond O. We need to look up the C triple bond O. And we need to look up the OH bond, right? And then multiply them by the numbers, use that formula right there, okay? All right, well, let's go back. Let me save this. Oops, okay, I'm sorry, that one. It's right there. Okay, so let me look the values up. So the values we have for the CH is 414, okay? So 414 for the CH. For the O double bond O is 498. For the C triple bond O is 1077. And there's one more that I can't fit in there, so I'll have to move it over to the right. 497 for the OH. Okay, so there's our 4 values. Now, what I'm going to do, I'm going to get rid of these Lewis structures here. I don't want to go to a new slide because I want you to be able to see what we're doing here. Okay. number of moles times bond energy or bond enthalpy. Okay. All right. So what we've done is we've figured out how many CH bonds we have, which is 8. I'm sorry. We're doing products minus reactants, not reactants minus products. So the product is CO and H2O. So CO, we're going to do 2 times CO is 1077. Okay, so when I say N of the product times bond energy of the product, really what I mean is how many of those total bonds are there? Well, we just figured it out that it's 2 of them. And then the bond energy, we looked that up, is 1077. The sum means you add them. That's all the sum means. This just means add. Total, okay? So the second product is H2O. The H2O has the OH bond, but how many were there? There were 8. So 8 times 497. Okay, now I'm going to close that parentheses out. Those are the products, right? So remember, each one was, this was 1077, and there were 2 of them, and then there were 8 of these 497s, right? Why 8? Because you have 4 times 2. Okay, now we're going to subtract the sum of the reactants. Remember, you do products minus reactants. Okay, and oh, I have to check that. Let me check that. It might actually be reactants minus products. I'm sorry. Let me just finish this first, and then we'll come back to it, and I'll explain it to you. So we had 8 of these bonds. 4 for the CH4, but there's 2 CH4s, so it's 8 times 414. Okay. And then we got 3 of the O2s. So the O2 is 498, so 3 times 498. Okay. It's actually reactants minus products, I'm sorry. So what I'm going to do is I'm just going to do products minus reactants and change the sign. But for the next example I show you, I'll do products minus reactants minus products. Okay, just a mistake on my part. So 2 times 1077 plus 8 times 497 is 6130. So I'm just doing what's in here. Okay. Minus, and then 8 times 414 plus 3 times 498, and you get 4806. Okay, each of these are in kilojoules per mole. So we take that subtraction, and you get 1324 kilojoules per mole. But I made a mistake. It's actually reactants minus products. So remember, A goes to B has the opposite sign of B minus A. B goes to A. So if we just want the opposite sign, it's actually minus 1324. That would be the correct answer. Why? Because it's actually the sum of the number of moles of reactants times delta, I'm sorry, times BE of the reactants minus the sum of the bond energies, sorry, end products times bond energy of the products. Okay, I got it reversed. Now, generally, when we do, this is why I made a mistake, we generally do products minus reactants. When we did thermochemistry, we did products minus reactants. But the way that these energies are measured is by measuring how much it takes to break the bond, not how much energy you get back to form the bond. So since we're using positive values for breaking the products, they're not actually breaking, they're forming. They would be the opposite sign. So for that reason, it's actually the reverse of what we're doing here. Okay, so there would be your answer, negative 1324, which is exothermic. Okay, so let me show you one more. But this one I'm going to do it with the correct formula. Okay. Okay, this one's a little simpler. I want to do one that's a little bit more complicated. Yeah, let's do this one. So here's the reaction, 2H2 plus O2. This is a simple reaction, but a little bit more complicated than the one that was there before. Okay, so again, I'm going to write this down correctly now. Delta H is equal to the sum of the number of moles of the reactant times the bond energy of the reactant. Okay. So reactants minus the sum of the number of moles of product times the bond energy of the product, PR for product. Okay. Put a little asterisk here. That's the correct formula right there. Okay. Hopefully we can see that now. This will give us the correct sign. The sign is important. We want to know whether something's endothermic or exothermic. Okay. So what I'm going to do, we don't know what energies they are. So what we're going to do is we're going to draw the Lewis structures first. So step one, do the Lewis structures. Okay, so you got H2. H2 is a very simple Lewis structure, right? So you know you have an H2 bond. So you look that up. H2 is 436. Okay. Now we've got an O2. Here's the Lewis structure. Again, I'm not going through the details of how to do these Lewis structures. That's something you'll have to do on your own. So that one's 498. And then the last one is the water. Here's the Lewis structure for water. Okay. Now what bond is in there? It's an OH bond, and the OH bond is 497. Okay, I'm getting that from, I'm using actually the data the Alex data table information there. Okay. There you go. Remember, an O bond, an O double bond O, a double bond between two oxygen atoms is not the same as two single bonds. So don't look up oxygen single bonds and then multiply by 2. Okay. Now, how many of these do we have? H2 has one bond, but there's a 2 in front of it. So it's really 2 times 436. Okay. So let's go through. Let's do the arithmetic. Again, we're going to do reactants minus products. So for the H2, it's 2 times 436, right? And then for the O2, there's only a 1 there. So it's just 1 times 498. Okay, so there's your reactants. Minus, on the product side, we just have water. Now, there's 1 bond, there's 2 bonds. And then you've got the 2 in front of it. So it's 4 times 497, right? And I'll put that in parentheses. So these are the products. Okay. So now adding the reactants together, 2 times 436 plus 498, you get 1370. Minus 4 times 497, 1988. Negative 618. Rounded to the nearest one. Okay, exothermic, right? Okay, does that make sense? So you're getting 2, it's 241. Oh, that seems a little, let me check that real quick. 2 times 242, 484. That seems a little off. Minus 618, that's what I get. Okay. It seems a little off to me. It seems like it should be around minus 400, but that seems to be the way it works out. So we'll go with that value, minus 618. There you go. Okay. So that, sorry for the mistake about doing products minus reactants. Remember, for bond enthalpy calculations, do reactants minus products. Okay. And there you go. All right. So that's the end of chapter 8. We've done all the Lewis structure calculations we can do. And chapter 9, I'm going to start on that tomorrow. Tomorrow's Thursday. I'll start on that. Chapter 9 is extra credit. And I recommend that you do it, but it is extra credit. There is no exam for chapter 9. It's just the homework that you have to do, but you get extra credit for it. And if I have time, I'll actually add in a little more for chapter 7 and make that extra credit as well. Okay. So have a great day and good luck with everything in terms of chapter 6, chapter 8, and then once we get into chapter 9, that as well. Take care.